In this video, I'm going to go over the Unit 7 Calculus review over applications of the definite integral. This would be equivalent to College Board's Unit 8, the second part of it. So first we're starting with area. So we're going to find the area bounded by this parabola and y equals x squared. So we've got an upside down parabola and a regular parabola. So we're going to graph, and remember you'll have your calculator to help you graph this. So here's our graph. We've got the x squared and then we've got the upside down parabola. The intersection is going to be at 3, 9. So for the area, we're looking for this area right here. Okay, so when we do area, it's always the integral. In this case from 0 to 3 of top minus bottom. So the top equation is going to be my 6x minus x squared. And then the bottom is x squared. Okay, now you can certainly do this by hand, do a power rule, all of that, but I am good with you using your calculator to get 9. Okay, next I'm looking at the region bounded by x equals the natural log of y plus 2, the vertical line x equals 6, and the horizontal lines y equals 1 and y equals 5. First, we're not going to be able to plug this into a calculator. So when I solve this equation, so y is going to equal e to the x minus 2. So again, you can graph this on your calculator. So we've got our grid here. We have a vertical line at 6, and then 2 horizontal lines at 1 and at 5. And then we're going to have that e to the x graph, which is gonna something like that. Okay, so our region that we're interested in is this area in here. Okay, now the reason this was presented as an x equals is it's gonna be easier to integrate going along the y-axis than it is to be on the x-axis. Now you could do that. You'd have to integrate from here to, you'd have to find that intersection. So we can integrate, you could break it up into this and then this, but we'll do this with respect to y. So it's going to be right minus left, so we're going to be integrating. We're starting at 1 up to 5. And then in this case, my right function is just that 6, and then minus, and we'll put this in parentheses, this equation in terms of x, so natural log y plus 2. And then we're just setting up the integral. So we're done. Right. Next one, we're going to find the area of this shaded region. And we just got to be a little bit careful about this. Essentially what we're going to do is we're going to take the area of the rectangle and subtract the area for the semicircle. So the area of the rectangle, we're going from -5 to 5, so that dimension is 10. And we're going from 0 to 4. So it's going to be 10 times 4 minus, for this part, we'll do the integral from -3 to 3 of our semicircle. Which gives me 25.863. All right, next up, we have polar area. So we've got two curves. We've got a 6 cosine squared, which is going to be this one, and an 8 cosine squared, which is going to be the bigger one. And if you're not sure, you can plug in a point, but the 8 one's going to be the bigger one. When we're doing polar area with two equations, we go from theta 1 to theta 2 of 1/2 the big one squared minus the little one squared. And what I mean by that is the outside minus the inside. If you were to do a cross section, it's the outside minus the inside. So for this one, we're going to be going from -pi over 2 to pi over 2. Okay, and then it's going to be 1/2 the outside one, 8 cosine squared theta squared, minus the inside one, squared. Okay, now we're setting this up, so we are going to go ahead and simplify. You could leave it like this if this was a free response, but it's not going to be. So I'm going to have 1/2. When I square this, I'm going to get 64 cosine to the 4th minus 36 cosine to the 4th. So you can either subtract and then divide by 2, or I'm just dividing by 2 right now. Okay, and so then if I simplify this, we get 14 cosine to the 4th theta d theta. Another polar problem. So we have this whole thing. The area shows polar curves. So one is 2 plus sine cosine, and the other one is 3 plus sine 3 theta cosine theta for 0 to pi. R is the region bounded by f of theta and the x-axis, which is going to be this one. But we're going to test a point anyway. And then S is bounded by the 2 curves. So just thinking, if I plugged in a test point like 0, if I plug 0 into this, sine of 0 is 0, so I get 2. So that's this one. Okay, and then in this one, if this is 0, we get 3 out of this one. But it did tell us. So we're going to find the area for R. R is just the area under F. So that's going to be the integral. And we're in polar, so we're not going from -2 to 2. That's a common mistake. We're going from 0 to pi of 1/2 r squared which gives me 6.480 using our calculator. Okay, next, the ray theta equals k, where k is between 0 and pi, divides S into 2 equal areas. We're going to write but do not evaluate an equation involving one or more integrals whose solution gives the value of k. Now, there's different ways that you can set this up, but essentially we're saying there's some ray that's going to split this area in half, so that this area is equal to this area. How I think about it is I'm just going to integrate from 0 to k and set that equal to the integral from k to pi. And the integral in polar is, of course, 1/2 r squared. Okay, and then for this, it's going to be the outside squared minus the inside squared. So since they're named G and F, I'm just going to use those, or you could plug in the equations, but I'm going to say G of theta squared minus F of theta squared is equal to the integral from k to pi of the same thing. Okay, now obviously we don't need the 1/2, so we could get rid of those if we wanted to. You could do like the integral from 0 to k is equal to half of the integral from 0 to pi. There's lots of ways that you could set that up, but this is how I set it. Okay, next we're going to talk about volume, and we're going to do a solid of revolution. So we're going to graph the region bounded by the square root of x and e to the negative 3x, and the vertical line x equals 1. Okay, once we have that, we're going to find that area. Then we're going to revolve it around the x-axis, the y-axis, and the line y equals 1. Okay, so let's graph. So I graph this on my calculator. Here we've got our square root, and then here's the e to the negative 3x, and then we have a vertical line at x equals 1, which we're imagining here. Okay, so So here's our regions. We've got the square root, the e to the negative x, and our vertical line at x equals 1. So we're going to be finding the area first, which is going to be the integral of top minus bottom. But the issue is my limits of integration are going to start at the intersection point. So I need to find that intersection. So I'm going to go back to the graph. Okay, and I'm going to find the intersection. So calculate the intersection. And I'm just going to enter, enter, enter. Okay, and I'm going to copy down all of those digits. Okay, so I'm going to label this point P, and I'm going to say P is equal to this value. Now, I'm going to need to use this value over and over and over again. So a trick is to store it in the calculator, because we're going to be using the calculator anyway. So if you go, I'm going to go ahead and type in that number, 0.2387341, and then I'm going to go to stow, which is above the on button. And I'm going to stow, and I'm going to label it P. You can name it whatever you want to, but I'm going to stow it in P. So then anytime I type in P, that value is stored in there. So I can use it in integrals, derivatives, whatever. I can also use it when I'm writing down my work. So that you can do this on the AP exam if you clearly label a value, or a function in that case. We can do that. So for our area, we're integrating from P to 1. So I can put the number P there, knowing that I've already defined that, from 1 of the top, which is the square root of x, minus the bottom. All right, so now we're going to do some rotations. So I'm going to take this same cross-section, and we're first going to revolve it around the x-axis. So it's going to be going here. My cross-sections need to be that. We're not going to have a whole lot of luck doing it the other direction. You could try, but it's going to be easier for my cross-sections to be just that. So if I'm going to rotate it here, we get a washer. Okay, because my cross-sections are going to be circles with circles in between. So big circle, little circle. Okay, so we're going to have, I'm going to pull the pi out. The integral, again from P to 1. And then it's pi r squared minus pi r squared, but I pulled out the r. And then it's going to be the top minus the bottom. So it's going to be the square root of x squared minus e to the negative 3x squared. Okay, or you can do the pi's with each of them, either way. Okay, now we're going to revolve it around the y-axis. Okay. So my outside minus inside, if I tried to do my cross-sections this way, that's a little bit challenging. So we're going to rotate it this way, and we're going to do this in terms of x, and to do that, we use cylindrical shells. Okay, so if my cross-sections are perpendicular to the axis of the rotation, we'll use washers. If my cross-sections are parallel, that's where we use our cylindrical shells. So that's going to be 2 pi times the integral from P to 1. So remember, it's 2 pi r. My r is going to be the x value, times the height, which is going to be the top minus the bottom. Next, we're going to revolve this around the line y equals 1. Okay, so y equals 1 is here. So we're rotating, going around that guy. So our axis is perpendicular, so we're going to be using washers. But we got to be a little bit careful because we're trying to find the outside radius minus the inside radius. So my outside radius, let me go ahead. We're still going to be integrating. I'm going to go ahead and pull that pi out. We're going to still be integrating from P until 1. And then it's going to be the outside circle minus the inside circle. So I need to figure out what the outside radius is, which is going to be from here to here. Okay, well, from here to here is e to the negative 3x, that dimension. But I want this distance. So if this distance is 1, and the distance here is going to be e to the 3x, that outside radius is going to be 1 minus e to the negative 3x. Okay, and then for my inside, we're going to subtract out the inside, which is going to be this dimension, which is going to be dependent on this one, and same thing. This distance here is the square root of x. This distance is going to be 1 minus that. Okay, which gets us 1.424. So you're always just thinking about the picture, thinking about how can we get those dimensions that we need. Okay, next we're going to look at the region bounded by x squared and the square root of x, and we're doing known cross sections. So we're going to do squares, semicircles, triangles with an altitude of 6, and equilateral triangles. So first, let's graph our region. Okay, so here's my region with x squared, square root of x, they intersect at 1, and our cross sections are perpendicular to the x-axis, and then we're constructing squares, semicircles, and so on top of that. Okay. For squares, so it's going to be the integral from 0 to 1 of the area of a square. Area of a square is just base times height, where the base and the height are the same. The base here is going to be top minus bottom, so root x minus x squared squared. Okay, dump that in the calculator. For semicircles, the area is going to be 1/2 pi r squared. Okay, so we're still integrating from 0 to 1. And it's going to be 1/2 pi. Now the radius. Okay, this dimension here is going to give me the diameter. So to get the radius, I'm going to take that square root of x minus x squared and cut it in half. Okay, so this 1/2 comes from the fact that we want just half of a circle. This 1/2 comes from the fact that this dimension gives me the diameter. Okay. Triangles with an altitude of 6. Well, area of a triangle is 1/2 base times height. So for this, we're going to be integrating from 0 to 1 again, and it's going to be 1/2. The base is going to be that root x minus x squared. The height for all of our triangles is going to be 6. Which gives us 1. And last, equilateral triangles. So the area of an equilateral triangle is the square root of 3 over 4s squared. So we're going to integrate from 0 to 1 of the square root of 3 over 4. And then that side is still root x minus x squared. Okay, next we have two equations. We've got 3 cosine x and e to the x. So my exponential one is going to be e to the x. And then that's going to be 3 cosine x. Okay, we've got R is the region in the first and second quadrants, bounded by the graphs there. So I'm going to go ahead and shade R is all of this. Okay, S is the region in the first quadrant. So that's just going to be this part right here. So it's the region in the first quadrant, bounded by the 2 graphs and the x-axis. Okay, so first we're going to find the area of S. And to find the area of S, we need to integrate from 0 to this point, whatever that is, of e to the x, and then we're going to integrate from this point to here for g of x. So I need to find this point and this point, and we're going to use the calculator to do that. So you want to graph and find the intersections, just like we did before. So the intersection, and I'm going to call this A. Okay, is going to be that. And then this one, I'm going to call B. Okay, so then when I'm referring to those, I can just use those two values. So for the area of S, again, it's going to be from 0 to A of e to the x. And then we're going to add that to the integral from A to B of cosine 3 cosine x. Oops, sorry. So from 0 to A of e to the x, and then from A to B of 3 cosine x. So this gets me 2.071. Now we're going to rotate R around the line y equals -2. So y equals -2 is going to be somewhere down here. So we're rotating it around that line. So my cross sections, okay, are going to look like this. Okay, so it's going to be the outside circle minus the inside circle. We've got a washer here. For my limits of integration, we have one more value we need to find. And I found that intersection to be a -1.496056. I'm going to call that C. Okay, so we're this one on top of this one the whole way. So we're going to integrate from C to A, because we're starting here, ending there. Now we need to figure out the radius. Okay, so we're going to have the outside radius, which is going to be from here to here. Okay, well from here to here is 3 cosine of x, but I want from here to here, so I'm going to have 3 cosine of x plus 2, since this is -2. Go ahead and put the pi on the outside. So the outside radius, 3 cosine x plus 2. We're going to square that. And then we're going to subtract the inside circle, whose radius is from here to here. So that's going to be this dimension, which is e to the x plus that 2. Which gets us 72.417. And then finally, same problem. We're going to do a known cross-section where each is an isosceles triangle with an isosceles right triangle with one leg across the base. So essentially, we're going to make a triangle here. The triangle, this dimension is going to be the cosine 3 cosine x minus e to the x, and then it's going to be squared. So my integral is going to go from C to A, and then it's 1/2 base times height, but both the base and the height are the same. So 3 cosine x minus e to the x squared. And I get 5.306. So now we have a region bounded by 1/2 x cubed, so that's that guy, y equals -2x, which is that guy, and y equals 4. We're going to write, but not evaluate, an integral that gives me the perimeter. So I'm going to start with the easy ones. Okay, so here this is -2, this is 2. So the first easy one to find is this dimension. So if that's -2, that's 2, that's going to be 4. So I'm going to say P equals 4 plus, you could do an integral for this one, but I'm just going to do the distance, well, really Pythagorean theorem. Okay, because this distance is 4. This distance is 2. So just using Pythagorean theorem, we can get that. For this one, though, we need to find the arc length. So my arc length formula is the square root, well, the integral from a to b, the square root of 1 plus dy dx squared. Okay, so I'm going to do some side work for this one. So y is 1/2 x cubed. So dy dx is 3/2 x squared. So dy dx squared is 9/2 x 9/4 x squared. So here I'm going to have the integral from 0 to 2 of the square root of 1 plus 9/4 x squared to the fourth. Dx. So that would give me the perimeter. So counting, Pythagorean theorem, arc length formula. Okay, another arc length problem. We're going to find the integral that gives the length of the arc to root x from 2 to 5. So I'm going to do my work over here. Okay, so this is going to be 2 times 1 over 2 root x, which would just be 1 over root x. So then if I square that, we get 1 over x. So my integral from 2 to 5, the square root of 1 plus 1 over x dx. Okay, here we're kind of going backwards, where I have the length of the arc is 1 to 10 of 1 plus 1 over x to the 4th. If the curve contains the point 1, 3, what is the equation of this curve? Well, let's start with this piece here is equal to dy dx squared. Okay, so that means dy dx is equal to 1 over x squared. Okay, which means my y, if I integrate, is going to be a negative 1 over x plus c. Okay, if I integrate 1 over x squared. Okay, then we're going to use our initial condition. To get that my c is 4. So my function is negative 1 over x plus 4. Okay. Next we have a total distance traveled in parametric. So a particle moves, we've got an x equation and a y equation. What is the distance it travels? So from 0 to 1. So my distance traveled in parametric is the integral from whatever to whatever of the square root of dx dt squared plus dy dt squared. Now, for this problem, option 1 would be to find these derivatives. Do not forget about the chain rule and plug those in, or type this into the calculator, type this into the calculator, and do this whole thing. Put this in y1, put this in y2, do the derivative of y1 squared plus the derivative of y2 squared, all of that. I'm going to go ahead and do it by hand, but either way works. You just have to be really careful with the calculator steps. So my dx dt, if I take the derivative of this, is going to be 4 cosine 2t times 2. And then if I do dy dt, that's going to be a negative 8 sine t squared times 2t. But again, you could store those equations into y1 and y2, do the derivative, so d dx of the equation x equals x, and then plug that in. But I'm going to go ahead and do it this way. So from 0 to 1. And then dump that in the calculator. So that was your Unit 7 review.